So now it's generated the mag file. We can go back to the layout. We can flush again, and now you'll see it actually generated the layout, and it's aligned the different transistors, and it made everything pretty. I'm just about booting up the new season of advanced integrated circuits that I teach in the spring, and it's time for another tutorial. And there's been some slight modifications from last year, so I'd like to walk you through that. And if you're not taking my course, then, well, maybe you'll find something useful. So let's dive in. Okay, so in the course, I have collected a set of IPs and collected a bit of scripts and programs and so on that we use in order to, well, simplify analog design. If you're a student of mine, then you have to install the tools locally. That is a rather lengthy procedure. It takes time, it is a bit tricky, it can go wrong, there's lots of things that can happen. So right now, today, we're gonna ignore that and do the impatient way. So the first thing we need to do is to get AIC26. So I'm just in a random folder, and we're cloning that recursively. So AIC26 is this repository. I'll put it in the link below, where I've collected the IPs that we need. And let's actually go to that repository location. So in the impatient section, you're going to run this command. And what I'm actually doing here is running Docker, because I've made a Docker container that contains the tools. But if you're a student of mine, you shouldn't use that. You should install the tools locally, because that's going to be more efficient. However, just for now, we're just going to run that script. Oh, we have to go into AIC26 first. And if everything works now, we should get a cyan looking terminal. Excellent. So now we're actually in the Docker container. I've connected to that via SSH. And let's just start the next terminal just to see that it actually is possible to run GUI applications. Okay, yes it is. Good. Okay. So once that's done, then we need to install a couple of tools. And these are Python scripts that I've made that in order to simplify the generation of IPs and simulation of IPs and also layout of analog integrated IPs in, well, it doesn't really matter the technology, but in this case, it's Sky130A. So what the system is doing now is installing the packages. While it's doing that, we can head over to the tutorial. So the goal of today is to go through the tutorial in detail, and I'll try to go slowly, although it's going to be hard, to sort of familiarize you with the way of designing in Sky130 and for the 2026 season. So this spring, it'll be, I think, the 5th year that I'm teaching the Advanced Integrated Circuit course at NTNU. That course has its own webpage. It's Analogicus AIC26. I'll put it in the description below so you can actually find it. And you'll also find the tutorial there. Okay, so now we have the IP setup. Let's actually look around a bit. So let's just do it like that. So now we're in the IP directory, and under the IP directory, you'll find a bunch of both tools and IPs. The names here, the CNR, the Janeway, or GNW, the SUN, Ripley, and so on, those are the different seasons. So if you have a look in, actually, let's start Emacs. If we have a look in this repository, let me just open up. So where did I put it? There we go. Temp AIC26 and IP config. Let me make the text a bit bigger. By the way, the text editor that I'm using right now is called Emacs. I'm old, as you can see from my gray beard. And I've been using Emacs for forever. I think these days I would highly recommend that you use either VS Code, or best case scenario is actually using Cursor, which is an excellent editor. And that it also allows you to use AI to help you a bit with the mundane stuff. So AIC is a collection of IPs and tools for analog design. So what we're going to do today is to create a new IP in this structure, and we're going to simulate, and we're going to have a look at how that works. So, well, this is the old video from last year. The video I'm making right now will replace that one. So let's create the IP. So this command is running the CIC-conf script. There's a new IP command. It's called X, just example. It's running in the project called Lilu. And technology is Sky130A. This is a technology that can actually be taped out on tiny tape outs. And we're going to run a template. So in this structure right now, well, a bunch of stuff just happened. It created a directory. But let's actually have a look at how this is done. In the IP tech Sky130, CIC-conf, Lilu YAML. That's the one that we gave a reference to just now. So this is just a method of creating files, because there is quite a lot of files that you need in order to run simulations and set up your system. So here there's just an info file. We'll get back to that content of that. There's a config file. We'll also get back to that maybe. And then in this structure, in this IP, I create some GitHub workflows in order to run a system, or run GitHub actions on GitHub in order to make it easy to design and figure out how things work. I just remember something, and that is that I already have a X folder. I'm gonna start again, and what you should do is ignore the thing I'm doing now, because I need to have a slightly different name than the one I have written before, but you should use the one that's in the tutorial. Okay, so let's go back to the tutorial. So I go through a bit in the tutorial what these different files are, how that works, why they are there, but we're not going to go too deeply into that now. What I want you to observe is that there are different folders. So there's a simulation folder and there's a work folder. For example, in the sim folder, in the work folder, that's where most of our work is going to be done. And it has a bunch of files. And the reason I have made these sort of structures is because the EDA tools, they require setup files. For example, Xschem, which is the schematic editor, it requires setup files in order to understand what to do and where to find the process design kit and the files that we get from Skywater. And the same applies to Magic. It also needs setup files. So it takes a little bit of time to do all this setup for a novice like you. It takes time for me too, but I'll try to make it simple. Now, the next thing we're going to do is actually create a repository on GitHub. So I'm going to go there, And this is my GitHub repository. I'm going to make a new one. And it's going to have the same name as I just created. Yeah, the description doesn't matter. And what I'm going to do now is set up the remote. So I'm going to go, I'm already in the GitHub repo. And now I'm going to add change my username. You should write your username, and you should use just the X without the 1. Okay. And now it's set up. The reason we need a GitHub repo is that for most of the GitHub actions, you actually need to run them on the server, and we need that for the docs. So the first we're going to do is actually change the docs. So there is going to be a README file in this folder, and the point of the README file is really to explain what this is. And you don't know this yet, but the tutorial contains a design of a current mirror. How? Well, it's going to be following the tutorial. The reason I like to force you to actually write in the documentation is that documentation is incredibly important as an analog designer. Think of documentation as a love letter to your future self. I've made designs 2 years, 10 years, 20 years ago. And the fact that at that time I've already learned that it's a good idea to write documentation means that I can still read and understand what I did 20 years ago. It's a fantastic thing because my memory, well, memory fades. Memory is like a sieve. Things disappear. But if you find strategies to write things down and store it permanently, then your life will be easier. So I highly recommend do proper documentation. On that note, lazy is not the right word. I don't like to do the same thing over and over again. I like to make my life as simple as I can. And one of the things that I like to do when I'm going to run commands and do stuff is to write the commands down. So in this work folder, you'll find a make file. So make is a program. So if I do just call make will look for a file called makefile. And inside the makefile, there will be rules that can be run. Now, I've created a default rule that when you just type make, it prints the help. So if I go into the work folder and open this makefile, you'll see it's actually pretty empty. But it includes another makefile from the technology library. So technology library is sort of this set of files on top of what we get from the Foundry that is supposed to make it easier to run the design rule checks and layout versus schematic and parasitic extraction and all the things that we need to do for an analog design. So for example, when I just run make, it will run the first rule in this makefile, and that happens to be help. So if I write make help, I'll get the same thing. Now there are other commands here. So for example, I can do make xview. That's another command. And if I do that, it should, if things work as we expect. Yeah, it ended up on a different screen. Let me pull it over. It opens up Xscheme. So Xscheme is the schematic editor we're going to use. So it might be a good idea to have a look inside and see how this makefile works. But for now, let's just go back to the tutorial and follow that. So, oh, yeah, right. So we're going to draw the schematic now. So actually, I shouldn't have closed down Xscheme. But let's open it up again. Note that your names and the names in the tutorial now are different from the names I have. That's simply because I already have this X library. So what we're going to do now is we're going to read the tutorial. So it says add ports. Now I already have some ports here. So instead of adding new ones, I'm going to just rename them. 5 micro. And let's actually let's make it a bit bigger so you can actually see what's going on. Now notice that, well, maybe you can't notice and it's not easy to see, but I find that right now Xscheme runs a bit slow. And the reason it's running slow is because I'm running this Docker container. Now the IBPS, so if we have a look in the schematic here that we want to create, actually that was the wrong way around. This is supposed to be 5 micro. So what we're going to make is a current mirror that takes a 5 microamp current in and provides a 20 microamp current out. So let's put that on this side, and this is an input pin. I want to change it into a output pin. Okay. And now I want to add some transistors. So let's look into the tutorial. So I'm going to do Shift-I. And then I'll get the select box. I'll want to go to this folder. And it'll say in the tutorial to go to, no, not that one, the ATR. And we're going to pick some transistors here. So these transistors have a naming convention where the first number, maybe it's too small to see, but it says 4C5FO. The 4C is, there's roughly 4 contacts on source and drain. And the 5FO, that describes it's roughly 5 times the minimum gate length. So I can place a transistor here, and if I press C, I can copy it. If I press C again, and press Shift F, I can flip it. But actually, before we go any further, the good thing about having a standard transistor library like this, is that you don't really have to do the layout of every single cell. I've done that for you. So if we, with Magic, which is the layout designer, open the C5F0, and it's going to be the mag file. Oh, Magic's going to be even slower on this Docker container. Yeah, it's incredibly slow. Okay. But it's going to work for you. Okay, there we can see the transistor. And let's see. If I press, is it? No, I still have to wait until it's loading. It's still loading. Blah, blah, blah. Slow, slow, slow. But if I select the layout window and I press V, it's gonna, or F. Is it V or F? No, it's V. To view the full screen, you can see the transistor, and here you can see the transistor gate, connection to the gate. The actual red here is the gate, and the channel will be in the intersection between the green parts and the red parts here. In the middle we have the drain, and on each side we have the source. So this transistor has 2 fingers. I like these type of transistors because even if I flip them vertically, then I have currents going in both directions, because it turns out that the direction of current in silicon actually changes the effective mass of electrons, and that can have an impact on the current in a transistor. So if you want something that's actually properly matched, you can either select to have all the currents in the same direction in the silicon, or you can do as I do here, just flip them, because then you have both, and well, it doesn't matter what you do with the transistor, and you don't have to be that careful, so it's nice. Now, I'm actually going to drop out of the Docker container because this is way too slow for a tutorial. So let me show you, and let me promote why you should install the tools locally. So now I've just dropped that in the same folder. We can go into the example folder, work, and let's run the magic again. Let's see, what did I call it? No, I want to look at the transistors. And I want the ends, I want the 4F50. 4C5, 5F0 mag. Okay, have a look now. Oh, you didn't see that, but it popped on my other screen. Did you see how fast it loaded? Compared to running in a Docker container? So, I would highly recommend that you install the tools locally. It'll be so much faster. And let's do the same for, yeah, I closed the next scheme. Let's open Xscheme also. Okay. So let's continue the tutorial. So what we want to do is draw this current mirror. So in Xscheme, you have to press the W command in order to wire. So let me do that again. You press the W. I can go down here and over here. Every time I'm changing corners now, I am pressing W. The bulks, they should all be connected to the source. That's not always the case, but for this current mirror, it is the case. And we want the source to be connected to VSS. And let's just route these up. And like that. And you might wonder, why are there two output transistors? Well, it's one of the reasons is that I want to be able to match as well as I can. Actually not match, but place the input transistor, this one, common centroid with the rest of the transistors. So I want this transistor to be in the middle. So I'm going to call it XO1. And I'm going to call this transistor XO0. But I actually want two transistors. And for the last one, I want XO2, no, 1, no, 2, 1, 0. So here I'm using bus notation. And let me zoom in so you can actually see it a bit better. I'm using bus notation on the name in order to get two transistors. So this is a good way to get multiple transistors. So in Xscheme, F gives you the full screen. Okay, so now we have our schematic. What we want to do now is, let's have a look. So remember to save. Yeah, we want a netlist. So here we can do mech xch cell lilu ex1. Mine's called the x1. And then we want to have a look at the netlist. And here you can see the netlist with our 5 transistors, which gives us the 1:4 ratio in the current mirror. Now we want to set up the simulation environment. And here also I'm using a script. Actually, let me do like that. And since my library is called the X1, I'm going to change those names and running. So what this does is copies a sort of typical SPICE setup, a typical SPICE file, a typical some other files that we have a bit of a look at. But if I now go into the simulation directory then we can see that again, there will be a makefile. There will be something called a CIC YAML file, because one of the things that is tedious with netlist simulation is that in order to change the process corner or temperature or voltage, you have to actually change the spice file. I don't want to do that. So I've created a Python script called CICSIM or 6sim to actually compute the permutations and run the different simulations. So let me just demonstrate an example of that. If I now write make typical, and let's have a look at what that does. So now we're going to go into the sim makefile, and you can see that this references another. No, that's the wrong directory, sorry. We want to go in here. That's makefile. Okay. So make typical, that's this one. First thing it'll do is it'll netlist. That can't be seen here because it's in the sim make. So let me show you what's in there. Tech. Let's see. Make. Sim make. Netlist. Ah. Interesting. So it'll do a netlist cell. A netlist cell will check for the whether there's an XCH directory under work. It will actually netlist the design, and if it's a layout view, then it might actually run the parasitic extracted. And afterwards it'll massage the spice file, because sometimes you get the wrong port order from, well, both layout and simulation. You probably won't encounter that. But anyway, so in order to see what a command actually does, you can add a -n, and then you'll see the same type of commands that you see in the makefile, and the last one is the actual running of the simulation. Now there you can see the simulation ran, nothing came out, but it ran. This 6sim actually will run ngSpice, but let's have a look at how it does it. So if we look at the output directory, then there's going to be a spice file in here. Actually, there's a bunch of files. You have a log file, which is log from ngSpice. You have another log from ngSpice based on the measurements. Because, okay, this is preemptive thing a little bit, but it's a very good idea to split up simulations into a actual simulation and parameter extraction, because what quite often happens when we're running analog simulations is that they take a lot of time. And for example, let's say it takes 24 hours to run the simulation. What you don't want then is that you've forgotten to add what's called a measurement of something. Maybe you've forgotten to measure a current somewhere or a voltage somewhere. And that you don't want to do you don't want to have to add that into the spice file and rerun the simulation. That takes a lot of time. It's much better to split it up and have the actual simulation in one run and the measurements in another. I'll show you how that works. But that is this log_m and mes file. The raw file is the actual waveform output. SHA file, let's have a look at that. So if nothing's changed in the input files in the spice file, let's open up the spice file, then there's no need to rerun the simulation. So in the spice file here, it'll include the actual spice netlist. And actually there will be quite a bit of stuff that you don't see, because there will be another spice file here generated by 6sim. And let's open that up. And in this spice file, you'll see it includes the actual PDK. Oh, there we go. It includes the PDK information. So here we have the transistor libraries for NFET, for PFET, and resistor and capacitor corners and temperatures and so on. Now, this is the part of the file that has to change every time you run a different temperature. So that's why there is this make file and the 6sim in order to, at least in my opinion, simplify that. So if I write make TFS, so typical fast slow, that may not be a familiar concept, but whenever we make a circuit design, we have to check that it works over different voltages, different temperatures, and different transistor corners, because it's impossible to make two transistors that are actually the same. Usually, for example, a ingot of silicon is cut into thin slices where you have the wafer. And that wafer has a certain intrinsic resistivity. That's because when you make the ingot, you mix in the dopants and you grow this ingot and you're turning it and so on and so forth. And when you cut the wafers, you end up with different resistivity. That resistivity might impact your transistor. Probably doesn't in a large degree, but maybe a little bit. And then in a factory or in the foundry, they will go through an insane amount of steps. It might take, well, let me be round. It might take many days. Multiple tens of days is how I want to describe it. From you start with a blank wafer until you actually have finished circuits. And each one of the steps, implanting boron or implanting whatever phosphorus, will have a certain precision. And that precision is not the same every day, every week. Which means that from wafer to wafer, you will have different transistors. And from within wafer, you can also have different transistors, because the lithography of just developing the circuit may have different patterns depending on where you are on the edge, depending on where you are on the wafer. All this means that we have to check what's called corners. So a fast transistor, a slow transistor, and a typical transistor. Ideally, we'd like to check all of them, all of the corners. Now, imagine that you had to run all these simulations here by changing the spice file and running again. That takes forever. That's why there is a 6sim, and that's why I'm forcing you to use this type of strategy. So what we're going to do now is we're going to add a few things to our spice file. So as of now, it's just a default spice file. Oh, sorry, getting back to this SHA file, that computes the hash. So a unique identifier for every single file in the input spice file, in order to, if the SHA hasn't changed or if no input file has changed, there is no point on rerunning the simulation. So if I write the same command again, it'll just skip it. And there's no change to the input file. It doesn't need to rerun. But let's change the input file. So first, let's delete the VDD. There's no point in that. We don't need it. We want to apply a 5 microamp current to the input of the current mirror. And now we want to measure the output of the current mirror. So as I said, we want to put the measurements in a different file in case we forget, or the simulation takes wrong and we forget to add something. So now I'm going to intentionally forget to add the measurements. Okay, so now the simulation has run. And here we can see it outputs a bunch of waveforms into the raw file. Actually, I'm going to add a couple of things here. So to make sure that we measure the current. Oh, it's already in there actually. Yeah, but let's add it anyway, just to be sure. Okay, before I do the measurement section here, Let's try and rerun. Okay. Okay, no, nothing has changed, and it doesn't rerun. So there's another file called mess, and this is where we put our measurements, because now I don't have to rerun the simulation to actually get the numbers out. So if I do it again now, it will not rerun the spice simulation. It'll skip it, but it will run the measurements. So imagine now that instead of a few seconds, the spice simulation actually took 24 hours. And now I can keep adding measurements if I want to. It may not seem necessary for these type of small files and small designs, and it's maybe not. But for big designs with long simulation times, it is worth doing. So yeah, please follow that. Now, sometimes you'll get into a corner where you might actually have changed something, but CIC Sim doesn't understand that. It happens. Then you can add this option. So make typical opt no SHA, and that will force a rerun of the simulation. Notice now that we actually get numbers out for the measurements. Now, I've made a way of summarizing the data. You don't have to use my way, but it is what I usually use, and the whole sort of setup is made around it. So the way it works is that you have this YAML file where you provide the specification for a simulation parameter. So in this case, it is the output current. We're saying that that's going to vary maximum plus minus 5% around a typical number of 20. And the scale here is microamps, so we're going to multiply the number by 1e6. And then use 3 significant digits, and the unit is microamps. If I rerun now, I don't think you'll see any difference. No, you won't. But actually, there's one difference, and that is that it'll write a CSV file with the results. At this point, we can open up, there's also going to be an HTML file that we can open. If you're on Linux, you have to use something else than open. Wasn't that there? Ah, there is a typo. Okay, just a second. I'm going to fix that typo. List otherwise I'll forget. No, that's 2026 lectures, tutorial, and result. Where is it? There we go. Okay, that's fixed. Yes, and the results will have, in this case, it's just a typical simulation. So it'll have the numbers for that. We could also have a look at the waveforms. And you can either use ngSpice or you can use SIGSIM. If I go to the output folder and just write ngSpice, I can load the this raw file, raw, and I can plot the current. That's one way to do it, and you can zoom here and so on. But I'm not a big fan of this waveform editor, so I made my own. And I'm not claiming it's the best in the world. If you find something better, please use that. There might be some not professional tools, but slightly better results, slightly better waveform editors these days. It's been a while since I checked. So this is the one I have. This is a search field. So if, for example, write V0, it will show the current, same as what we have in had in ngSpice a few minutes ago. Note that this field is actually a regex search field. So if I write IV0, it won't find anything because the parentheses are a special character in regex. But if you add an escape character, it will find it. And I can also, for example, take out the gate voltage of the NMOS, diode-connected NMOS. Maybe it's better to have them in separate plots. So if I do that and add axis, and now I can see them both. So that's what I usually use to look at the waveforms. Okay, now we want to run all the corners and check how our circuit behaves. So it says in the tutorial that we don't need to change the voltage because the current mirror doesn't have a VDD. It only has a ground. So I'm just going to not run the multiple different voltage corners there. And we're going to do typical, extreme test condition, and Monte Carlo. Monte Carlo is a way of simulating the randomness of the different transistors. So here you would set, well, actually inside the SPICE model, they have set a certain distribution for the threshold voltage and mobility and so on. And then the Monte Carlo method will select randomly from that distribution and simulate your performance, such that you can actually get an idea of what will my performance be when you get the circuits back. It's very important to simulate both corners and also Monte Carlo variation. It's maybe, I would almost claim that it's more important to simulate Monte Carlo than corners. At least for student designs. Okay, now we've run all the corners. There is also a way of running Python files after the simulation has been completed. So in this folder, you will find there is a tron.py. And let me just show you quickly how that works. So the reason for that is sometimes it's not possible to do everything in ngSpice. Sometimes you kind of want to do more advanced calculations. In this case, it'll open the YAML file, and let's have a look at what that's about. So for every single simulation that has been run, let's see, let's do KTT, TT, VT, YAML. So here you'll have the results. You have the current and you have the voltage. So that's what we load here now. So what I could do, for example, is object to say IBNS 20 micro, and let's add a unit to it, and let's just take a float number for the object that is IBNS 20 micro and multiply it by 1e6. Okay, so if I run again, you'll see now that it computes another value. So you can use this Python script to modify the information or extend the information that comes out of ngSpice. I use that sometimes if you have temperature sweeps or something like that in the ngSpice and you want to collate them into a single array. This is a way to do it. The tutorial shows an example on how to plot, for example. And these Python script will be run after a simulation is completed. Now, we can also make a summary. That creates a README file. If you have Pandoc installed, then we can take that README file and generate a HTML file. Wait. Oh, we need an O. And open that up. And here you can see the full simulation. Now you notice that it also highlights that our current mirror violates the spec. It's outside what we expect. There are multiple ways to fix that. One way to fix that is to go into the Rambo file and say, well, I don't want 5%, I want 20%. You change the spec. And if I now rerun, oh, actually, I have to not just do that one, but do that one too. And now you can see it turned black. So everything's okay. So when you get a parameter that is outside what you expect, then it's a... you can either choose to fix the design, or you can choose to fix the spec. Now, if you've been given that spec from somebody, you can't just fix the spec and then say it's okay, right? If you've been given it, then you have to talk to them. I'm gonna take a little bit of pause now to change the window. Just a second. Okay, so what I wanted to jump to was chat, and I didn't want you to see all my chat history. But I'd like you also to ask ChatGPT, write a verification plan with common items for a current mirror design. So as you do your designs, then I would recommend that you use chat in order to help you make the verification plan and figure out what type of simulations should you be doing. So let's see what it says for a current mirror. Reference current. Okay, so that's the input. This is interesting, right? So it says, well, you should check for a min and max range for the input current. That makes sense. So maybe in my design here and in my simulation, I should not just have a corner for the voltage and the temperature and so on, but also change my input current and check that if my input current, for example, is very high, do I get the same 4x current output. Check the mirror ratio. Maybe we should try and compute that. So if we go to the measurements file, how would we do that? Let's go to the spice file. Let's open the spice file also. So we would need to know the current in the input. And that's actually... I'm thinking. I just got the rest. I haven't done this for the current mirror before. So the verification plan you're seeing now, I'm seeing it for the first time also. So I need a bit of time to think, because I kind of want to add the current corners. So if I go into the CIC sim, let's have a look at the... Maybe I should write a... This is param I input equals 5 microamp. And if that's the typical, then I high might be, let's say, 6 microamp. And I low might be, actually, let's do 2.5 and let's double the current. Okay. And now if I go over here and I say, and let's go to my make file, and I need to add the AT corner, and here I want to add a low, a high. Now it's definitely going to fail now, but let's just say check if it works. Okay, So that gives the same result. Let me change that I input to 6, because then we should get a different number out, 24, I guess. Yeah, okay, so now we can see that works, 24. So now we have a way of checking for multiple different currents what are well, how the circuit's going to work. Now we want to check the mirror ratio. So here, it's a bit tricky to get the parameters into a design. So I'm going to cheat a bit. And I think it's isn't it a B source that I can say VI input, VI input, and set that to 0, and just say that that is, actually, let's just do a voltage source. So what I want to do is have something where I can get the input current, in this case as a voltage, and I'm going to save it. This is a trick to get parameters into the simulation. The VI input. Because now in my measurement file, I should be able to do let IBN, no, let's say, what do we call it? K equals minus IV0 divided by VI input. And let's just do that at the end. K. Find K at 5 nano. So let's see if that works. That failed. Why did it fail? Oh, right. So we already have that source. I need to call it something else. V1. Okay. Where's our K? 4.1. Perfect. So that tells us that our current mirror is not perfect. It's 4. More than 4. So that's interesting. And you can see here, as you continue down, you can add more and more values. So here, for example, I out minus K IREF divided by K IREF. Let's add that. That's fun. Let's let's, what do we want? So we actually want accuracy to be the absolute value. Let's see if we have that function in ngSpice. I think so. What is it? IBN. You can actually just use IBN here too. IBN minus K times let IREF be VI input. K times IREF divided by K times IREF, and let's get the accuracy at 5 nano. Let's see if this works. Oh, that's 0. Why is it 0? Well, so wouldn't that always be 0? Since we compute the K here, should we ask it? No, let's not do that. But anyway, based on a verification plan like this, you can figure out what your circuit should, what sort of simulations you should do on your circuit to prove that it actually works. Now, we're not going to do much more here, but you can also see that it says simulation matrix as in process corners, Vmin, temp, and different IREF and output voltages and output voltage sweep and so on. This is excellent. It's a really, really good tool to help you, guide you towards how you should verify your design. It even specifies that for different Actually, let's test that. Let's see if we can write. You can maybe also just use it to generate the spice file, right? Let's see if it makes something that's sensible. It even knows that control is written in the entity spice. You could use level 1, but I don't think that's a good idea, but fine. Let chat continue. Okay, so let's see what it generates. Params, okay, we can VDD, yeah. IRF, okay. Now this you'd replace with the actual design. The model you don't need. Wow, it even has Gmin, for convergence issues. That's really good. That's impressive. And then the different simulations. So I'd highly encourage you to use chat to help you learn about spice and how to do simulations. It's an excellent way. And you can see that it actually knows how to do it. Or at least infers how to do it. But let's get back to the tutorial. That's a bit of a digression. Highly encouraged. Right. This is viewing the results. Okay, now we're at the end. Now we've simulated our design. We know that it works. We're happy with it. And we're at the stage where we actually want to physically make it. What do I mean by physically make it is that you can't give the schematic to a factory or foundry. You actually have to make the layout. So we're gonna open the layout file now. Mag. And yours going to be named differently, right? Okay, so here we have an empty layout file. So let's see what the tutorial says. Yeah, okay, I'm not going to go through much on Magic. I encourage you to look at I think there's some videos here, and also you need to read you need to read the manual. And there's no way around it. It is needed. There's a lot of hotkeys. Magic was written, I don't know, back in the 80s. It's written in C and Tickle. It's insanely fast, actually, compared to modern tools. And it's actually quite good. I like it. It has the fastest design rule check in existence. The modern tools are much more slow. Although you can do much more advanced technologies in the modern tools, though. So we want to add transistors. It says you can do cell place instance, but I actually like to do cell manager. No, that's not it. Library manager. There we go. And hopefully we can see our transistors here. And I can take one of these and I can place it. Okay, now we have a transistor. We need to zoom out. And I can press S to select it. And now comes the incredibly tedious part of copying. And zooming in, and let's see. If I place a box with a left mouse button, right mouse button, press X, I can see if this is correct. And then I need to unselect it. And now you see I have DRC errors. You see that? Okay, so this is going to be finicky. It's going to take time. And there maybe? We'll see how it looks. That maybe looks okay. And then we take another one and we copy that. And then we do it again. And this is exactly the type of thing that I detest. It is manual work, it takes a long time, and the wonderful thing is that magic files are text files. Let's actually save this file now. So, save. And let me open it and let me clean up the screen a bit. By the way, I don't know if I mentioned that earlier, but you don't have to use Emacs. Actually, please don't. You should use Cursor or a VS Code. It's just I'm too old to change. Actually, I do use Cursor quite a bit. It's excellent. Okay. What you see on the right side now of the screen now is actually the layout file. So I can actually change things here. Let's see, use that one, box 92. I think if I change this number, for example, to 100, and then we say flush Lilo EX1, you will, oh, that didn't change much. Let's say 1000. Flush. I was hoping it moves. It didn't move. Okay. Maybe that was a bad example then. Yeah. But what I was trying to demonstrate is that you can actually change numbers here and get things that move. But it didn't want to do it for some reason. I don't know why. Nope, didn't want to do it. So even though I changed the numbers here, it didn't do anything. Maybe it's the different number. No, that's correct. Okay, that didn't work. Okay, maybe this one then. Okay, yeah, that worked. Okay, fine. So I just wanted to demonstrate that you can actually change the text files and it will affect your layout. It will do stuff. Now, you can see that the file format on the right side is not that difficult. It's pretty easy. What's slightly more tricky is to go from a schematic like this to generate the layout. So luckily you don't have to do that. I've already made a script that does that for you. And if you type this command in the work folder, oh great. Oh right, yeah, because I have the EX1. Okay, so now it's generated the mag file. We can go back to the layout. We can flush again, and now you'll see it actually generated the layout, and it's aligned the different transistors, and it made everything pretty. So highly recommended for placement. Let's actually remove some of the actually, let's see. So in a layout like this, if you haven't seen a layout before, then all the different colors represent different three-dimensional structures. So in this case, the blue is the first metal layer. It's not actually called first metal layer, it's called local interconnect. And then the, well, I don't know, yellow? Maybe? Yellowish color? Orangey color is the first metal layer. but actually it's called metal 1, but it's a second metal layer, so it may be a bit confusing, but anyway. All these different layers you can see on the left side here. So, and here you can right click to deselect them, left click to select them. You can turn the visibility on and off, and that sometimes helps to make it a bit more easy to see what's going on. You can also do those commands from the screen here. Actually, we want that one. See no star, that returns everything off. And then I want to see via local, see local interconnect, see M1. I wonder if I can do this. 1, M2. No, you have to do one at a time. See via 1 and see M2. So now we can see where it connects. So here, for example, we have local I that connects up to the metal 1. And now we can actually start routing this design. Because if I now, well, the DRC you can see is clean after placing. But if I run layout versus schematic, then it fails. Why does it fail? It shouldn't fail that horribly. Permission denied. Interesting. Just a second, I think I might have a bug. Actually, core. I know why this happened. Okay. The reason I'm getting problems now is that when we took out these files, then I was running in a Docker container, and the file permissions are not you can see it here. It's not able to set those cross not cross. Reset. So it's not able to set those permission in Linux, and then it's the same in the Mac. That's maybe something to be aware of. But if I now go in here and my CDL, LVS, then it should all work. Yes, okay. Well, it should work, but it's to give you incorrect. If you didn't understand any of that, don't worry. Now, we want to route this design. So the first thing we want to do is add a ground. So let me clean up the windows a bit. So Magic has this nice feature of a grid. So if I turn the grid on and I snap the grid, then it's much easier to draw things that are exactly 1 micron by something wide. If I now press the middle mouse button on top of that, then it'll paint those rectangles. I can do undo. You can also just write paint local I, and that has the same effect. Now, actually, I want to turn off the snap to grid off, because now I want to route, and I need to press spacebar in order to change to the wire tool. And now I can just click like that. I left click, I route, I left click again, and then now I right click in order to disable. And here it'll actually pick up the right metal layer. As long as it's not above multiple ones, it'll usually pick up the right one. So if I click on top of the metal 1 here, then it'll, as you can see, it will route in that metal 1. And if I now press shift and the right, it will step down or create a via down to the layer below. And now I've routed the source connection. Now, you have to keep in your head the different connections though. That's a bit unfortunate, but that's how it is. Okay, now we run around the gates. Same thing, just click and all the gates are going to be connected together. I want this middle transistor. So right now I'm doing Shift X. So I want this middle transistor to be our diode connected transistor. But I don't want to connect in metal 1. I want to connect in the local eye. The reason I want to connect in the lowest possible metal is that one of the things that can happen to... Oh, by the way, what I'm doing now is pressing Shift and the arrow keys. It's a bit slow maybe, so I can do like this. Shift and arrow keys to change my rectangle and just painting. The reason I want to do it in local interconnect is that I want to connect the drain to the gate in the lowest possible level, because every time you add a metal layer, there is what's called a chemical mechanical polish that happens on the wafer. And this chemical mechanical polish has the tendency to induce charges into the metal. Now those charges, if they're picked up by the gate, could actually cause damage, because you can break the covalent bonds, like, well, in a oxide, which is an amorphous crystalline or random collection of random distributed collection of silicon and oxygen atoms. In that type of structure, you can actually have dangling bonds. That means you have missing connections to other parts of the oxide. In those boundaries, or in those missing connections, it's kind of like you have what's called a dangling bond. It is a possible state for an electron to jump into. Usually those dangling bonds are negatively charged, so they add hydrogen in the silicon oxide in order to sort of tighten those or fill those holes. But those hydrogen bonds are very weak and it's easy to break. Now those can break and you can actually create a dangling state, or a dangling bond, or a vacant state where electrons can jump into, and this can actually change your threshold voltage. It's also possible to generate something called Frankel pairs, which is, you should think of it like, usually in an amorphous silicon oxide, you have a mix of silicon and oxygen. It's sort of, yeah, different places of the atoms. The oxygen atoms can actually wander. They can sort of break out of the structure and get lodged in places there shouldn't be. And now you end up with like one positive hole where there should be an oxygen, a vacancy, and the negative ion of the oxygen that is somewhere else. And these type of oxygen vacancies can also generate possible states for electrons to jump into and change your threshold voltage. Now we don't want any of this. So we kind of want under processing that there is the least amount of charge change. Now the reason you connect the gate to the drain is because the drain has a diode to ground, the diode to the substrate, or in most technologies at least, which limits the voltage that you can get on the gate. So that's why we want to connect the drain to the source in the lowest possible level. Now we want to hook up the drains, and in this case it's a very good idea to decide to route metal 1 in only vertical direction, and metal 2, for example, in only horizontal direction. And if your structure done that, then it's much more easy to route up big designs. Now I broke that rule right now. It might not be easy to see, but see no local eye. So here you can see I broke that rule. I went horizontal and then vertical in metal 1. But that's okay. There's no way I'm going to go through here with another metal. So that's okay. I can't get through there anyway. So that's, yeah. Not always do you need to think too much about the decisions. Now this placement that I've done, you will see that it adds the ports by itself. Yeah, and I think I'll keep them like that. So now I want to save the design. And let's check. Hey! CDLS, now it's correct. We're done with the layout. Yay! Now we want to extract the parasitics, layout parasitics, because when we have the actual layout, it's possible to back annotate the capacitances and resistances. In this case, almost for all the designs that are doing in Skywater, not all the designs, but it's most common to extract only the capacitances. For most designs, like low frequency designs, it is sufficient to have the capacitances. Sometimes we do include the resistance, parasitic resistance also, especially for power nets and things like that. So things that consume a lot of current, you need to extract RC. And then for really high frequency stuff, you may even need to extract inductances also. And I promise you, those type of simulations take forever to run. There's not much difference between just a standard simulation and the simulation with capacitance, so that's okay. And here you can see that there is now a capacitance between the input net and the output net of about 2 femtofarads. And that's probably because they run parallel. Actually, let's try and change it. So let me make it a lot worse. Let's see, how do I make it smaller? So now I'm holding in shift and I'm scrolling on my wheel to make the metal width smaller. And let me route up here. So what I'm trying to demonstrate now is that I should now get an increased capacitance between ground. Oh, actually, this is actually ground. It's not. Okay, let's go around then. Like that. It's still DRC clean, so that should be okay. And let me check that my design's still okay. Yes, it is. Okay. So let's see. I had 4 femtofarad from the output to ground and 13 from the input to ground and 2 femtofarads. Actually, let's save this. It's a different file. Nilu. No, wait, just a second. Nilu EX1 LPE V1. Okay. And let me extract the parasitics again. And let's look at those 2 files side by side. Okay. So now you can see that I've doubled the parasitic capacitance on the right side here between my output net and my input net. And I've actually reduced the capacitance to ground, and I've almost doubled the capacitance from the output net to ground. So the way you do the layout affects to a significant degree these parasitics, and that you have to think about while you do a layout, especially for coupling between sensitive nets and what we call aggressors, like clocks and stuff like that. Let's see, what is the next step now? Okay, so now we want to run... Yeah, we have to change to the layout simulation. So then we have to go to the simulation makefile. So if I go to the sim folder, Lilu, makefile, and let's change the view from schematic to layout, which means that when I run my simulation now, I need to be in the sim folder. Make all. No, wrong directory. It will now run all the simulations. You can see that all the measurements still work, and that's good. Oh, right. See here? It cannot find the parameter I input. So I probably have a mistake in my makefile because we added that parameter. So that's this one. I forgot to add it on the ETC corner, and I need to also add it on the Monte Carlo corner. Let's try it again. Yep, that works. Okay, usually for was what is usually for layout. Unfortunately, every time you generate a new parasitic extracted netlist, it's usually not the same as last time. I don't know why, but maybe the date changes or something. Is there a date in these files? Let's have a look. No, there isn't. But it's almost like there's a stochastic component, because at least the SHA sum is not the same every time. So if I run typical now, it will generate the parasitic extracted netlist. But if I rerun, it will run again. So somehow, okay, you saw that it changes. Let's rerun it. Yeah, you can see it actually changes. So I don't know why there is a stochastic component here. Maybe there's some hash tables or something. I don't know if the names change, but clearly stuff changes inside this extracted netlist, which is why the simulation will always be rerun. I haven't looked into that, how to fix it, or if it's fixable. If the names change here, then yeah, there's not much I can do. Maybe that's something to talk to Tim about, Tim Edwards, who is maintainer on Magic. Anyway, so I want to add the layout results to my summary table. Let's see, summary. Now the summary, that sort of collects all the results, and I'm going pretty fast through these files, but you will need to have a look when you get there. Here we have the schematic results, and we have the layout results. All these feed into Python script in CIC Sim, so it's possible to go inside and figure out how it works. If it doesn't work, well, you can contact me, and hopefully I'll have time to fix it. So let's make the summary. And if I now create the README file again, and I think I have it in the background here, you can see now we have also the layout files. Now, interesting, right? Because now we change the input current from, what did we change it from? I don't remember. Yeah, 2.5 to 10. So obviously my ETC corner will change quite a bit, and it'll be out of spec. But that's maybe something you need to find different. Well, we don't need to do that now. Right. Let's have a look at what the next step is. Okay, make documentation. Important. So first of all, we want to add all the documentation. So all the results. Didn't work. Okay, I need to be in this folder. Yeah, because I'm using a different folder. Don't worry, it'll work for you. Yeah, I want to read me file. All the commands on the right side of the screen will work for you, I hope. Okay, now we've added the simulation results. There's also a file in right next to the schematic in design. Lilu here and markdown. That should be generated in the documentation. So if I write that, okay. Now we're gonna get the GitHub actions to work. So we have to change the info.yaml file. Let me do it like this now. And let's see. Yes, that's yes. My name is not anonymous. Nor am I a member of Anonymous. And my email, well, that you can find anywhere on the interwebs, so you can see it. That's not dangerous. And like that. And then we want to make the documentation. So here mine will be X1, Sky130A, and then I want to generate the layouts for, no, not layouts, but schematics for that cell. Actually, it's called the X1. Okay. So if I now write git commit, let's say git status. So this whole thing is in a git repository. Notice that the magic files have not been added. So those we need to add. And we don't want the CIC file, but we want that one. Okay, the other files here are not that important. Let's and oh, yeah. There was some things there since we're using Linux and it had master as the default branch, but I want main as the default branch. If you run into that trouble, well, you've now seen how to do it, if you can decode it. So if I go to my Git repository, I should now find the X1 tutorial. Okay, what we want to do now is set up GitHub pages. So let's see, actually let's do that quite quickly. So you should see settings and then pages and then GitHub actions. Okay, good. Because now these actions, they run. So you can here you can see that we can go inside actually. It will try to make a GDS. Now a GDS is a layout stream file. So it is the exact file that you send to the Foundry, and here it will initiate a Docker container, and it'll actually run, check out your design, and it'll take out the layout. Once it's done with the layout, you can actually download it. Let's see if it's done already. If I go up here, maybe if I go up to actions, GDS, and then at the bottom here, you can actually download the GDS. That was a bit small. Is it really that small? Usually they're a bit bigger. It'll be a zip file, and inside the zip file we'll have a GDS. We can open that with Klayout. Is it starting? Yes, it is. Just a bit slow. La 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 la. Okay, while that's waiting, we can also check the LVS. So it'll run the same layout versus schematic, and it'll, oh, there we go. So you can see the layout. So this is in Klayout, and you can see that it's the same layout as we draw. And yeah, these different actions are very useful because they tell you whether your design actually is valid for somebody else. It also creates the documentation. So if I go to my repository now, I go to About, I can use my GitHub pages and save that and then jump here. Okay. So after a while, these will turn green. But here we can see my README file. You can see how to actually just take out this IP. You can see the layout. This might not work. Let's see. Let's leave that loading. Oh. And then you'll see the schematic. Hopefully. No? No schematic. That's interesting. Okay, there might be a bug. But you'll see also the simulation results. That's annoying. Why didn't that work? What I wanted you to see was... it should look like this. So you should see the schematic. But for some reason that didn't work. And it also looks like the 3D viewer no longer works for some reason. Okay. Something to maybe fix then. So that was a quick introduction to the tutorial. I'll put the links in the description below. And was there anything else I wanted to touch on? Let's see. No, I think that's it. Hopefully you find this useful. Good luck with the project when you get there. And have fun.